In this video, I'd like to talk about the aufbau principle and the periodic table. In the previous video, we learned that in the hydrogen atom, all of the sublevels in a given principal energy level are at the same energy level. However, we also learned that as soon as you place one additional electron into the atom, that these sublevels begin to split. That is, the 2s sublevel is lower than the 2p, the 3s sublevel is lower than the 3p, which is lower than the 3d, and so forth. So our goal here is to describe the electronic structure of a polyelectronic atom, an atom with two or more electrons. To do that, we're going to use what's called the Aufbau principle. Aufbau comes from the German verb bauen, which means to build. Aufbau literally means to build up. And the idea is that we build up the electronic structure of a polyatomic atom by adding electrons into hydrogen-like orbitals. We place the electrons in the lowest energy orbitals that can accommodate them, and when a sublevel is filled, we simply go to the next available one until we've run out of electrons. Now, the electron configuration then, once we've done this, is a list of which sublevels are occupied and how many electrons are in each sublevel. Once we have written that, we have solved our problem. We have described the electronic structure of a polyelectronic atom. Okay? To do this, we also need what's known as Hund's rule. Hund's rule, you may recall, says that the lowest energy configuration has the maximum number of unpaired electrons by the Pauli exclusion principle in a set of degenerate orbitals, meaning orbitals at the same energy. You'll recall the Pauli exclusion principle says that you can place up to 2 electrons in the same orbital as long as they have opposite spins. Hund's rule basically says when you are placing electrons into a sublevel, place 1 electron in each empty orbital with the same spin. Only go back and pair up electrons in an orbital when you need to. And when you do that, they must have opposite spins. That will give you the maximum number of unpaired electrons. So let's do an example of this. Here is the energy level diagram for a polyelectronic atom, and let's take the example of phosphorus. So we're going to describe the electronic structure of an atom of phosphorus in its ground state. And by the way, for now, if an atom obeys the Aufbau principle, we say it is the ground state electron configuration. That's what we're concerned with now. So to begin, I need to know how many electrons are in an atom of phosphorus. So I go to my periodic table, and I see that phosphorus has 15 electrons in it. So I'll begin, in accordance with the Aufbau principle, at the lowest energy sublevel that can receive these electrons, which would be the 1s sublevel. 1s1, 1s2. The up and down pointing arrows with pointing in opposite directions indicate the electrons with opposite spins. 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2, 3p1, 3p2, 3p3. That would be an energy level diagram for a phosphorus atom. Now, to describe that by writing an electron configuration, I would simply list those sublevels and then specify with a superscript how many electrons are in each sublevel. So the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p3. You'll recall that the noble gas abbreviation says that I can take the electrons corresponding to the configuration of the previous noble gas, which in this case would be neon, the first 10 electrons, and abbreviate those with the symbol of the noble gas in brackets. So an alternative and completely acceptable way to express the electron configuration of phosphorus would be neon 3s2, 3p3. Notice that one advantage of the energy level diagram is that it lets us predict, quite accurately in fact, how many unpaired electrons are in an atom of an element. Based on the half-filled 3p sublevel, we would say that an atom of phosphorus has 3 unpaired electrons. And that is the case in its ground state. Now, you may ask yourself, do I have to memorize the order in which the sublevels fill? 1s, 2s, 2p, 3s, 3p, 4s, 3d, etc., etc. And the answer is no. And if you had me for your first year of chemistry, you will recall the coolest thing in chemistry is that the size, structure, and shape of the periodic table, the dimensions of each section, correspond exactly to the order in which the sublevels fill and the number of electrons that can fit in each. And as this diagram shows, you should consider a stretch of elements on the periodic table as corresponding to filling a particular sublevel. So for example, from the elements boron to neon, we are filling the 2p sublevel. From rubidium to strontium, we are filling the 5s sublevel, and so forth. Since you have the periodic table at your hand, you use that as your guide for writing electron configurations. A couple of important concepts. The idea of valence electrons. Valence electrons are described as electrons in the highest occupied principal energy level. If you look at your electron configuration and recognize that the number before the type of orbital represents the principal energy level in which that sublevel exists, you simply look and see which sublevels have the highest numbers. Any electrons in them correspond to valence electrons. Okay? And as you'll see, that is in the outermost S and P sublevels only. If you write the electron configuration for an atom that has electrons in S, P, and D sublevels, you will see that only the S and P electrons are in the highest occupied principal energy level. Okay? And therefore, because it only corresponds to S and P, an S sublevel can hold 2, a P sublevel can hold 6, an atom can have between 1 and 8 valence electrons. So if we go back to our previous slide and look at phosphorus, we'll see phosphorus has 2 electrons in the 3s sublevel, 3 electrons in the 3p sublevel. The third principal energy level is the highest occupied principal energy level, so a phosphorus atom has 5 valence electrons. And by the way, that would be true of any element in group 15 because they would all have 2 electrons in an S sublevel and 3 electrons in a P sublevel. Core electrons, on the other hand, are all the other ones, the ones that are not in the valence shell. So let's do some examples of writing electron configurations. For each of the following elements, we're going to identify the element, give its ground state electron configuration, state the number of valence electrons, and the number of unpaired electrons in an atom. So the alkaline earth element in the same period as silicon. The alkaline earths you should know are group 2 elements, and the one in the same period as silicon is magnesium. So using the noble gas configuration, I will write the configuration as neon 3s2. The 2 electrons in the 3s sublevel are its valence electrons. So I've got 2 valence electrons. And the number of unpaired electrons can be determined by looking at a partial orbital notation diagram, which is kind of like an energy level diagram, but it only shows partially filled sublevels, which would be the 3s. And because the 3s is completely filled, there are 0 unpaired electrons in an atom of magnesium. The third element of group 15 is arsenic. Oops. Not argon, arsenic. Using the noble gas abbreviation, I will write the electron configuration argon 4s2, 3d10, 4p3. That has 5 valence electrons, the 2 in the 4s and the 3 in the 4p. The 4p sublevel is partly filled. It has 1 electron in each. So we would say that an atom of arsenic has 3 unpaired electrons. Element number 116, I must have written this problem back before they gave it a name because we now know that it is actually Livermorium. This is complicated because this is after the actinide, so we're going to have to go all the way back to radon. After radon, the 7s sublevel fills. We jump down to the 5f sublevel corresponding to the actinides, and we completely fill that, 5f14. We then jump back up to the 6d sublevel and completely fill that, 6d10. Then we continue into the 7p sublevel, and to get to element 112, Livermorium, we need to put 4 electrons in the 7p sublevel. Now, there are lots and lots of electrons after the radon configuration, but only those in the highest occupied principal energy level count as valence electrons. Not the 5f electrons, not the 6d electrons, but only the electrons in the 7s and 7p, because they're in the highest occupied principal energy level. So that would be a total of 4 valence electrons. And to count the unpaired electrons, placing 4 electrons in the 7p sublevel, 1, 2, 3, 4 in obeyance of Hund's rule, that would give me 2 unpaired electrons. Let's do a few more examples. An element with 4 unpaired 5d electrons. Well, if I go to the 5d sublevel, which starts with lanthanum, 4 electrons would take me to tungsten. So I can write the electron configuration of tungsten as xenon 6s2, 4f14, 5d6. I'm sorry, 5d4. And only the 2 electrons in the 6s sublevel count as valence electrons, so that's only 2 valence electrons. The 5d sublevel, which contains 5 orbitals, is partly filled with 1, 2, 3, 4 electrons. So as we specified, 4 unpaired electrons. But there is another way we can have 4 unpaired electrons in the 5d sublevel. One is to have 4 of the 5d orbitals singly occupied and the remaining orbital empty, or 4 of the 5d orbitals singly occupied and the other orbital full, which would be the case for osmium. So there are 2 elements that fit this description. Osmium's electron configuration would be very similar with just 2 more electrons. Xenon, 6s2, 4f14, 5d6. Still only 2 valence electrons. And now 1, 2, 3, 4, 5, 6. 4 unpaired electrons. Finally, the halogen with electrons in 5p orbitals. The 5p sublevel corresponds to indium to xenon, so the halogen would be the group 17 element, or iodine. And I'll write the electron configuration. Krypton, 5s2, 4d10, 5p5. 2 electrons in the 5s sublevel, 5 electrons in the 5p sublevel give me 7 valence electrons. Make that a little clearer. Here's my 5p sublevel. If I place 5 electrons, 1, 2, 3, 4, 5, that leaves me with 1 unpaired electrons. Okay, now, up to now, we have been dealing only with atoms in their ground states. What's an excited state electron configuration? Well, an excited state of an element is one in which electrons are not in the lowest energy orbitals that can accommodate them. They have been excited to higher energy orbitals. So an electron configuration is any electron configuration in which the electrons are not in the lowest energy levels available to them. And that would imply that it is not following the Aufbau principle. Okay, so let's do some examples on the next slide. I give you 3 electron configurations and ask you to tell me whether it represents an excited state configuration. In either case, whether it does or does not, let's identify the element and rewrite the configuration to represent the ground state. So in the first example, I've got 1s2, 2s2, 2p6, 3s2, 3p6. So I've filled the 3p sublevel with 6 electrons. And then I put 3 electrons in the 3d sublevel. Is that the ground state? No, it's not, because we know that the 4s sublevel fills before the 3d. So we'll rewrite this in the ground state. 1s2, 2s2, 2p6, 3s2, 3p6, and the remaining 3 electrons, 2 will go into the 4s, 1 will remain in the 3d. I look on the periodic table and see which element has 1 electron in the 3d sublevel, and that would be scandium. In the next example, neon, 3s2, 3p4. Sounds good to me, and that's sulfur. In the final example, krypton, 5s2, 4d5, 5p2. That is the correct order in which the sublevels fill, but I don't want to put electrons in the 5p sublevel until I've completely filled the 4d sublevel, which can hold 10 electrons. So I'll rewrite this into the ground state. Basically, I'm dropping the excited state electrons into the lower energy sublevels that still have room for them. 5s2, 4d7, which is our friend rhodium. Okay, in our last video in this unit, we will talk about periodic trends and atomic properties. See you then.